Hi everyone, and welcome back to our Lean Six Sigma series. Today we're diving into the measurement phase in the DMEC framework. Now, think about any trip you've taken. Before you hit the road, you probably checked a map or GPS, right? Knowing where you are starting from is just as important as knowing where you're headed. That's what the measure phase is all about, understanding your current process performance in concrete data-driven terms. So why is measurement so important? Let's be honest, without data, all we've got are guesses. And in Six Sigma, we don't guess. We measure. The measure phase is where we figure out exactly how things are currently working. It's our starting point for change. We take the ideas from the project charter and start validating them through actual data collection. It's also the stage where we spot performance gaps and figure out if our current process can even meet expectations. By the time you're done with this phase, you should have collected enough data to paint a clear picture of the current state, set a concrete improvement goal, and understand how capable the process really is. That sets the stage for the next phase, analyze. But first, we need to measure. Let's explore the tools that help us do that. Let's start with something really intuitive, the check sheet. If you've ever kept a tally during a game, you've already used one. It's a structured form that helps us collect data in a consistent way. Simple? Yes, but incredibly useful. Check sheets are great when you need to see how often something happens, machine breakdowns, defects, delays. They're especially good when you're just starting to understand a process. The following are the basic steps in developing check sheets. Agree on the type of data to be recorded. The data could relate to the number of defects and type of defects and apply to equipment, the operator, process, department, shift, and so on. Decide which characteristics and items are to be checked. Determine the type of check sheet to use, for example, tabular form, defect position, or tally chart. Design the form to allow the data to be recorded in a flexible and meaningful way. Decide who will collect data, over which period, and from what sources. Record the data on check sheets and analyze data. As one example, you might use a diagram of a product and mark where defects occur. That way, patterns literally jump off the page. Training for this is minimal. Most teams pick it up with hands-on use. Next up, histograms. Think of these as a more visual way to understand your data distribution. Instead of staring at rows of numbers, you group those numbers and show them as bars. You'll see right away if your data is skewed, has a clear center, or if it's all over the place. There are 8 basic steps in developing histograms. Collect enough data points for establishing a representative pattern. Subtract the smallest individual value from the largest in the dataset. As a rough guide, take the square root of the total number of data points and round it to the nearest integer. For example, for 50 data points, divide the range by 7 and 125 data points by 11. The resultant value determines the interval of the sample. It should be rounded up for convenience. Calculate the number of data points in each group or class. Plot the histogram with the intervals in the x-axis and the frequency of occurrence on the y-axis. Clearly label the histogram. Interpret the histogram related to centering, variation, and shape or distribution. For example, let's say you're measuring car fuel efficiency. A histogram might show most cars get 20-30 mpg, but a few outliers hit 40+. That skew tells you something important. Run charts help you look at how a process performs over time. You track one metric, say monthly production, and plot it. If it goes up, down, or cycles, you'll see that pattern. There are 4 basic steps to developing a run chart. Select the parameter and time period for measurement. Collect enough data to identify meaningful trends. Generally, the x-axis is for time or sequence cycle, whereas y-axis is for the variable parameter that you are measuring. Plot the data in a line graph along the x and y-axis. Interpret the chart. If there are no obvious trends, then calculate the average value of the data points and draw a horizontal line at the average value. As one example, say your packaging machine had efficiency swings. A run chart can show if the process is stable or if something changed. But don't overreact to every wiggle. That's where control charts come in. Control charts are run charts with muscle. They include control limits to show if a process is stable or has unusual variations. There are 6 basic steps in developing control charts. Choose the quality characteristic to be charted. Establish the type of control chart to ascertain whether it is a variable chart or an attribute chart. Choose the subgroup or sample size. Decide on a system of collecting data. The automatic recording of data by a calibrated instrument is preferable to manually recorded data. Calculate the mean and standard deviation, and then calculate the control limits. Plot the data and control limits on a control chart and interpret results. Please note that if a point jumps above the upper limit, something special happened. Investigate. Don't ignore it. A Pareto analysis is useful to identify a characteristic that is currently experiencing a high number of nonconformities. The 80/20 rule lives here. Pareto charts show which causes contribute most to a problem. Fix the top 20% and you often eliminate 80% of the issues. There are 5 basic steps in developing a Pareto chart. Identify the general problem, for example, IC board defects, and its causes, for example, soldering, etching, molding, cracking, other. Select a standard unit of measurement, for example, frequency of defects or money loss for a chosen time period. Collect data for each of the causes in terms of the chosen unit of measurement. Plot the Pareto chart with causes along the x-axis and the unit of measurement along the y-axis. The causes are charted in descending order of values from left to right. Analyze the graph and decide on the priority for improvement. These charts are important because they can tell you where to spend your time as a project manager. For example, let's say soldering defects are 40% of your problem. Focus there first. Don't waste time chasing the 3% outlier. Now let's talk relationships, specifically between 2 variables. A scatter diagram shows if there's a correlation between them. For example, as temperature rises, do complaints go up? Or is it random? There are 5 basic steps in developing a scatter diagram. Collect paired samples of data of 2 variables that may be related. Draw the x and y axes of the diagram. Plot the data points on the diagram. If some values are repeated, circle those points depending on the number of times they are repeated. Interpret the results. The scatter diagram does not predict cause and effect relationships. It can, however, indicate a possible positive or negative correlation or no correlation between 2 variables. For example, if heavier cars consistently have lower MPG, you'll see a downward trend. That's a negative correlation. It's not cause and effect, but it's a strong clue. Cause and effect diagrams can be leveraged in both the define phase as well as the measurement phase. Also called Ishikawa diagrams or fishbone diagrams, these are brainstorming tools. You start with a problem, like late shipments, and then explore all possible causes. There are 9 basic steps in developing a cause and effect diagram. Select the most appropriate cause and effect format. If the problem can be isolated to a single section or department, choose either a 6M small team or a CDAC large team approach. Define with clarity and write the key effect of the problem in a box to the right-hand side of the diagram. Draw a horizontal line from the left-hand side of the box. Draw main branches, fishbones of the diagram after agreeing on the main categories of causes. Brainstorm for each category the potential sub-causes affecting the category. List the sub-causes of each category in a flip chart. Rank the sub-causes in order of importance by a group consensus or multi-voting and select up to 6 top sub-causes for each category. Construct the diagram by posting the top sub-causes in each category. These are the root causes. Decide upon further dispersion analysis or gather additional data needed to confirm the root causes. Develop solutions and improvement plans. These diagrams are amazing for team brainstorming in either the define or measurement phase. Use sticky notes, whiteboards, whatever gets your team thinking. Finally, process capability tells you if your process can meet customer specs. CP is potential. CPK is actual. There are 4 basic steps in process capability measurement. Using a stable control chart, determine the process grand average, the average, and process standard deviation. Determine the upper control limit and the lower control limit based upon customer requirements. For a stable process, assume that the values of the sample, mean, and standard deviation are the same as the corresponding values of the population. Calculate the process capability indices CP and CPK. As a general rule, if your CPK is below 1.0, your process isn't cutting it. You'll miss specs. Above 1.33, that's usually acceptable. The measurement phase is a fundamental portion of the DMAIC process. And as a project manager, it's your job to ensure that this portion is given the respect and care that it deserves. Each tool we went through can give you a piece of the performance puzzle. Use them wisely, and you'll be ready to uncover the root causes in the analyze phase. That's it for the measure phase. In the next unit, we'll turn this data into insight. Now, let's go through the measurement tools in slight detail so that you can apply them to your project as you see fit. See you again in the analyze phase.